simulation to be able to do lensing better, I guess.
Yeah, thanks a lot. Thanks for having me. So I am Andrew Zentner. I am very happy to be here. I'm going to be talking a little bit about issues that both Gary and Sarah talked about in their talks. And I don't know how far beyond the obvious it is, but it's definitely something that I think deserves a little bit more scrutiny. So I'll just begin by acknowledging my collaborators on this project. So primarily Douglas Rudd, who was a student at Chicago and is now at the IAS. And I'll also begin by apologizing. If any of you were at the substructure workshop last week, I'm going to use the same joke again. Because I developed that joke specifically for that talk, and then I realized how more broadly applicable this joke was.
Did you get it last time? Maybe they didn't.
They did get it. Oh. I wouldn't have recycled a bad one. But, so...
Let's be the judge of that.
I guess that's true. It's a different... You might be a tougher crowd. So, this is kind of funny already, I think. Now I've lost my train of thought. It's all in the delivery, too. So lots of times what happens is that if you're modeling something in detail, particularly simulations, it's very easy to sort of pick at all these things that people want to do and sort of be very curmudgeonly and say, well, you can't do that, you can't do this, you can't do that. And I'm going to be talking about simulation work, but I'm actually going to hopefully change the tone of the discussion a little bit. And I think that there are a lot of detailed things that require a lot of detailed simulation work, but that we can actually bring these goals to fruition. And the global thing here is basically that anytime we're measuring something with a few % accuracy or less, a lot of details matter that we probably didn't have to worry about before. Okay? I was going to begin now with a sort of brief introduction to why weak lensing is constraining dark energy. So basically the goal, the object here is thinking about weak lensing survey, shear convergence power spectrum as a way to constrain dark energy. But Gary already talked about this basically, so I can kind of breeze through this, I assume. And basically the idea, and I'm using sort of W models, particularly W0, WA as sort of benchmark models. Really it's the dynamics that I'm talking about that are the thrust of my talk. So that specificity is not really too relevant for what I want to talk about today. But basically the idea, and I've taken some wild models here, some pretty wildly varying models here just to illustrate the point, is that when you have a lot of recent acceleration, the distance scale in the universe is dilated. Okay, so this is just angular diameter distance versus redshift. Likewise, when you have more matter, there's more growth, more structure growth at late times, normalized to the CMB at high Z. And when you have less dark energy, or dark energy that turns on more slowly, or more dark energy, or dark energy that turns on more slowly, you have less structure growth. Okay? And basically, a weak lensing power spectrum is measuring some combination of those effects. And that's how you are constraining these models. You have pretty much a featureless power spectrum. You can see sort of this nonlinear bump a little bit here, around L's of, say, I don't know, 4, 5, 600, something like that. But you basically have a featureless power spectrum, and how much it's raised up or down by structure growth or side to side by length scales in the universe. It's constraining your cosmological model. Okay? And that's just sort of an example spectrum. And the basic idea, and these projections have been done by a lot of people, is that any set of future experiments, I don't want to advocate any future experiment, just as a guide, will measure some combination of what's called W pivot. So the value of W at that scale where it's best measured. Yeah? No, what's up?
Oh, just okay. An explanation. I mean, what we found is that everything seems to be in the amplitude of that. We did test some parameter estimation. We just take a power law.
The amplitude of this.
And then there's nothing from shifting, but almost all the information comes about distance versus redshift comes from the amplitude.
The amplitude of this, yeah, exactly. Yeah, that's right. But the primary thing you're sensitive to from your paper actually is the distance scale, right? D of Z.
It's not due to any shifting. It's because of what the distance does in the lensing curve to the amplitude.
Right, yeah, it's the efficiency factor, yeah, exactly. It's the efficiency factor in the lensing. It's how efficient each individual perturbation is that you're integrating over.
Right.
Yeah, that's right. So I didn't mean to imply that I was just taking something and shifting it. Just
okay. I mean, it's surprising to me to find out that actually with the power law you get the same result. There's really it's not anything from any standard candle in there.
Right. It's just that distance ratio factor.
Right.
That's exactly right. Yeah. So the point here is just that if you do any number of these projections, you have W pivot, you have WA. W pivot is the thing you're interested in, I think, because you just, basic question you want to ask is, can you rule out a model where W is -1 and constant, right? Just always -1. And that just says that DES, SNAP, LSST, these things would constrain W to a few percent. Okay, I'm doing that kind of quickly. Gary already talked about that. And now we'll get to the point of basically what this talk is about, is that there are galaxies in the universe. They tend to complicate things. Okay, unfortunately, I'm being a little sarcastic. We know about that. Those are the things being lensed, right? But they make the predictions a little bit more difficult. Okay, that's the upshot here. So what we did, what actually Doug Rudd did most of this work as part of his thesis project. He actually designed a set of simulations that, for a reason that had nothing to do with this, and we kind of realized that we could apply it to this problem. But the basic idea was to take 3 simulations, okay, all begun from the same initial phases, all begun from the same initial conditions, okay. In one simulation, simulate only the gravitational physics. So basically, that's just a dark matter, an n-body simulation, what we always call n-body simulation, just the dark matter physics, just the gravitational physics. Okay. In the next case, add non-radiative baryonic physics. So you're treating the hydrodynamics, but you're treating the gas in such a way that it can't lose its kinetic energy. It can't radiate away its kinetic energy. Okay. It actually does exchange energy. It shocks and things like that. In some of the literature, you'll see this as called adiabatic, non-radiative. It's basically the same thing. And in the last case, we added the things that tend to be a lot more fishy, but that actually give you galaxies, which are prescriptions for how the gas cools, how it forms galaxies, what supernovae feedback there are, things like that. We didn't explore any parameter space with respect to that model. It's impractical to do so right now. But we just have one example of what such a model might look like. Okay, so that's the basic idea. 3 simulations, 3 different sets of physics. Probably something like this being closest to the reality. Okay, because there's observational evidence for galaxies. And we saw what happened. Okay, so the first thing you do, or not the first thing, but one of the things you might do, is to look at just a convergence power spectrum. Right. So this is a plot that, I know it's a little bit complicated, a little bit hard to read, but on the y-axis it's a residual of a convergence power spectrum as a function of multipole. I don't know, I have a little shadow there. But it's basically the convergence power spectrum from these 2 other simulations, the non-radiative gas simulation and the galaxy formation simulation. Okay. And Lloyd, you did this already analytically for the hot variant, which I guess would be like the non-radiative gas type simulation, compared to the n-body result. So the n-body result, in other words, is 0 across this plot. Okay? And basically, the point here is that when you have non-radiative gas, you have some increase of power. And I'll get into why we think that why these things are happening. You have some increase in power on intermediate scale, say around L of 1,000. Eventually, it cuts off. And that's sort of what's basically known about the hot gas in clusters, I think. It's basically that you have some floor, some inner floor, and there's sort of a dearth of hot gas compared to all matter in the centers of clusters. Okay. If you look at the galaxy formation simulation, you have an enormous enhancement in the power. Okay, and that's this blue line here. And that's basically because you're forming a galaxy inside that halo. And it's rearranging matter, in fact, on very large scales. Okay, and I'll come back to that. So the basic point is that compared to the statistical errors of some of these future next generation experiments, these effects are large, okay, kind of obviously large. The relevant way you might, depending on what you're interested in, the relevant way you might quantify large is just in estimating what biases they give you in cosmological parameters. Yeah? They have the overcooling problem, yeah. So that's a good point. So I actually wanted to say that. So that's a standard problem. It's related. Well, I guess it's not shown that it's related. I think it's related to what Sarah mentioned, the disk formation problem. But basically, it's that galaxy formation simulations now typically produce galaxies that have stellar masses anywhere from 30 to 100% greater than the galaxies that we observe in the real universe. So in some sense, this is the worst case scenario. And that's why it's actually useful to look at the whole spectrum. Because the truth is probably somewhere in between here. We don't actually know. Okay, we can't actually predict to that accuracy. And in that sense, if you think about it that way, it's basically, this is a whole talk about one parameter, one line on one of Gary's slides, which is basically how well can you put a prior on P of K. Okay? You're still always going to get the geometrical information out, but you want to say how well can you put a prior on P of K. Okay. So that being said, you can go back to now asking how is this relevant for something you might care about if you're interested in dark energy parameters. And here, I'm taking W0, WA. And I'm using I'm plotting it this way because you can imagine as you go to smaller and smaller L's, these effects become less and less important. So the most naive thing you could do, and it's actually not too different from some of the more sophisticated things that Hooter and White have tried, is just to start cutting out information on some scales. So don't use that, just use linear power. So here's a plot of bias. This is bias on both of these axes. This is W0, this is WA. This is bias measured in units of the projected statistical bias. So it's the absolute value of the bias divided by the statistical error. Okay? And basically the point here is that anytime you're going beyond L's of a few hundred, okay, and this is for the cooling, the galaxy formation simulation, the biggest possible effect, okay, you would have significant biases that are several times your statistical error, your projected statistical error. Okay? And that's the whole point, the whole reason to be worried about it, is that you potentially could exclude the right model if you were just completely naive about this. In practice, it probably wouldn't happen. Because in practice, you see sort of a feature, this feature, like in the galaxy formation simulation. Okay? You notice that something kind of weird was going on. It'd probably be a bad chi-square. You notice something weird was going on. So in practice, you might not realize these biases. But if you were completely unaware of this, you would just say, well, something weird is going on. Okay? So that's the basic point of why to look at this. You can ask the simple question, which is, what if I just now say, okay, if I go out to L's of a few hundred, I can bring the bias down below the statistical error. So just excise small scales. And I've shown here the simplest case, where you say, as a function of L max, again, the smallest scale or the highest multipole you're going to use in your analysis, how the errors degrade relative to going out to an L max of 3,000. Okay? So in other words, compare your error as a function of maximum multipole compared to the error you would get if you used all information out to L of 3,000. That's why they all converge at 1 down there. WA, W0, and omega dark energy. Then you can see that by the time you get to L's of a few hundred, then you've lost a factor of 2 or 3 or something like that in your information. So you're not doing much better than you would do just from the geometrical tests, okay, just from the geometry constraint alone. Okay. So the hope is, the goal is, the idea is, well, maybe we can do a little bit better than that if we can put some prior on how we understand what's going on with the power spectrum on sort of quasi-linear and nonlinear scales. Okay, so it's like having a prior on P of K in Gary's talk. Okay. And that's what the rest of this talk is basically about. It's describing that effect, seeing what you can do about it. Okay. So probably all of us know that the basic unit, or I'll talk about it at least this way because of a surprisingly simple, or not too surprising, but a simple result that I'll show later. The basic unit of nonlinear structure is the dark matter halo. Okay. That's one of the things that goes into all these predictions. What's the profile of a halo? Because you're usually using the halo model. So you determine your clustering statistics by knowing the clustering of halos and then the internal structures of halos. Okay. So this is sort of the basic building block of your nonlinear structure. The degree to which you don't know what your halos look like affects you over a wide area in multipole space, simply because something that's confined in real space is broad in Fourier space. And that's basically it. And why do we see this strong effect in the galaxy formation simulation? Again, that's simple. Turns out the analytic approximations don't work, but they convince you that at least you should expect something like this, which is just something like the contraction of the halo in response to the formation of a cold component at its center. Okay. The basic idea, the usual analytic approximations are all based on adiabatic contraction. Adiabatic contraction is just the idea that if you have some angular momentum component and you build up mass inside a circular orbit, that orbit kind of shrinks in response to the slow buildup of mass. Okay? So in other words, you compress the mass of the halo along with the building of a cold component at the center of your galaxy, the center of your halo. Okay? So that's kind of obvious. It turns out that in detail, the contraction is not adiabatic. Okay? So you can't actually model it to within any sort of worthwhile accuracy using this model. But you can simulate it. Okay. And the hope here is that, so I kind of realized last night I didn't have a plot that just showed profiles, so I kind of made one ratty example of one profile. The hope here is that you don't actually need to know the details of what the galaxy looks like to get at relevant observables. In other words, power spectra on multipoles of a few thousand. Because you're not actually probing the internal structure of the galaxy, whether it's a disk or whatever. Just probing by how much are you moving the mass around on large scales in the halo. Okay. And what I mean by that, so this is a plot of the density profile of a halo. You probably have all seen something similar to this before. The n-body halo, so this is one example of one halo. The n-body halo is the black line, which is kind of here. It's kind of close to this red line on this plot. And you can see just by looking at this density profile plot that spans many orders of magnitude, that the galaxy formation simulation has a huge density increase, enhancement at the center. That's just the formation of the galaxy. It's more obvious, easier to look at the differences with the non-radiative, in the non-radiative case, in this relative plot, where it's the residual in the density as a function of distance, a function of radius, distance from the center of the halo. And what you see, and the thing that's not encapsulated in any sort of adiabatic contraction model, is that even at the 10s or 20% level, there's a large rearrangement of mass out to beyond the virial radius of the halo. So this is roughly in units of the virial radius. Even beyond the virial radius of the halo, there's something like 10-20% effect of just rearranging the mass in response to the formation of galaxies within the cluster. Okay. And that's the basic point. Now, of course, this is just not an arbitrary change to the power spectrum. So it's not just like taking some band powers and just letting them float arbitrarily. We have some understanding of why this is happening, how it should be happening. In fact, you can use this concentration sort of nomenclature that's used to describe halos. We tried a lot more complicated things before we realized that this is actually good enough. We use this concentration nomenclature, which says to plot the concentrations of halos. So this is total mass here, and just dark matter here, for these same three simulations. I don't know if it's as clear being up close as it is for all of you. The black line is the n-body simulation. The red is the non-radiative gas simulation. And the blue is the galaxy formation simulation again. So the same color scheme. And the basic point is that on relevant halo mass scales, so 10 to the 13, 10 to the 14 solar masses, groups and clusters, things that you're actually measuring the structures of when you're measuring the convergence power spectrum, you have a large change, enhancement, in the effective concentrations of the mass distribution. Okay? And you can very effectively actually model it with only this one parameter. Okay? So I can model that simulation, treating it as the true data, only by introducing now, or I shouldn't say one parameter, but only through a modified concentration mass relation. I've assumed that relation to be a power law in mass and redshift. Okay? And that works very, very well. In a sense, I'll tell you the sense in which it works in a second. So we originally tried much more complicated things, multi-component halo models, all kinds of stuff. But obviously, it's just basically measuring the concentration of mass. And because this transition from r to the minus 3 to r to the minus 1 in an NFW profile happens so slowly, it actually doesn't matter if you kind of let the inner profile float, because you can just, it's degenerate with having just a very high concentration. Okay. So it's very simple why this works, I think. And here's just a demonstration. The particular power spectrum, for simplicity, I think this is the one where I just said I had a sheet of sources at z of 1, okay, and modeled it. But basically the point here is, well, I should say, actually, I've now inverted the plot, so I have to explain. Now, this is a residual with respect to the galaxy formation simulation, whereas before it was with respect to the n-body simulation. Okay? So now this galaxy formation simulation that used to run up on this plot in relative power spectrum is now the 0. Okay? So the n-body simulation now is running down. It's just, so the opposite of what I showed in the earlier plot. Okay? This red line is this galaxy formation model, where I've taken the n-body halos and just put on them artificially a modified C of M relation, a modified concentration mass relation, and then recomputed what I would get for the power spectrum, for the convergence spectrum. You can see out to L's of a few thousand, that works pretty well compared to sort of the accuracies of which we're interested. And this is just the limitation. You can see the jaggedness here. That's just the limitation of that simulation. Okay. So to within what I can tell, what we can tell, that simple model seems to work very well. And as a practical matter, what I mean by very well is that if you now churn through and ask what are the biases once you've modeled the simulation, treated the simulation as a true data set, and modeled the simulation in this way, the biases are about 10% or less, depending on the parameter of your statistical uncertainty. Okay, so it works pretty well. And it's very, very simple. I just have a couple more slides in like a couple minutes. So then the obvious thing is that you can't have more information, right? You have to have a degradation in what information you're getting out of the observable, because now you have extra parameter freedom. Okay? So if you want to measure, for example, your uncertainty in W, so this is your uncertainty in this new model where I've added extra degrees of freedom, compared to the standard case where I've just assumed that I know P of K infinitely accurately. Okay? If I allow it to vary according to this mode, where it's only the concentrations of halos that are changing this power spectrum, then if I stick to this power law model, then I have degradations of something like 10 to 15%, even in the worst case. Okay. So, and that was adequate for this simulation. The other exercise I did, I actually didn't put the plot up, was to just allow for an arbitrary bin relation. So in other words, C of M in a whole bunch of different bins, varies from bin to bin, varies as a function of redshift. And even that does pretty well. That's sort of like a 50% degradation in these parameters. So even if you allow for a fairly arbitrary C of M relation, so you're saying that the power spectrum can only vary in as much as C of M lets it vary. But that C of M relation can be pretty arbitrary. And you're only degrading the amount of information. In other words, what you're getting about dark energy by a factor of something like 50%. Okay. So I thought that was pretty successful. And the other interesting thing that you're obviously getting for free, and I'll just, since I only have a couple of minutes, I'll focus on one panel here, is you're getting these galaxy formation parameters. In other words, the whole problem was that you didn't have a galaxy formation model that you trusted well enough to predict power spectra on relevant scales. But now you're just measuring what those parameters are. When you're looking at the convergence spectrum, the only relevant parameter seems to be this concentration. Okay. But somehow that's telling you about how galaxies form inside of halos. It's not exactly clear what that's telling you, but it's telling you something. It's some constraint that any galaxy formation model will have to meet. So what this plot is showing is, on the x-axis, and I'll just focus on this panel here. On the x-axis, this is the power law index of the mass dependence of the C of M relation. This is the pivot concentration. So in other words, just like the pivot W, there is some concentration at some mass, which is about 10 to the 14 solar masses. There's some mass at which this concentration relation is most well determined, the mass that is most sensitive, the mass that is most affecting convergence power spectrum on scales of about 1,000 or so. Okay, that's 10 to the 14 solar masses. The interesting thing is now you can constrain the C of M relation to within a few percent. Okay, 5 to 10, something like that, 5, 10, maybe 20%, depending on the details and assumptions and something like that.
Here, you assume you know the mass function?
Who's asking me that? Yes, Vermont, yes. I've assumed that I know the mass function. Actually, that's a good point, because there's another paper, and even in our paper, there was some effect of not quite having, the halos not quite having the same virial masses, not quite having the same biases. To some degree, we think that it's kind of lucky that this concentration canceled out that effect. In other words, if I let the concentration float and just fit the simulation, it incorporates some of what that effect is. So it's not completely just taking a C of M relation. You see what I mean? But that's something, that's future work. I mean, that's exactly what we want to get at. Yeah. Yeah. In principle, so what we've done, actually, I forgot who did it, but it's been done several times before. The convergence power spectrum out to L's of a couple thousand is just not very sensitive to the scatter. But if you go out further in multipole, or you go to 3-point function, then yeah, you would measure that. Yeah?
So at the moment, I thought that the reason we measure concentrations in clusters and groups was because we had the high resolution space-based data to get the small scales and high galaxy density. So why is it that SNAP and DES seem to do comparably well at this particular program?
Well, here what they're doing is they're measuring it statistically, first of all, right? But what they're doing is they're measuring something that is a local configuration space. So in some sense I agree. They're not measuring so for example, in strong lensing, you're measuring where the mass is actually at the center of the halo. And here you're basically not sensitive to that. You're sensitive to exactly how this outer profile is sort of slightly shifting when you change the concentration.
So you don't need to see the Baryonic flux, just where the profile
Yeah, that's exactly what you're measuring here. And it's a fairly localized in configuration space, and you're actually measuring this spread into Fourier space.
So are you including the concentration, I guess, should also vary a bit with dark energy, even in the dark matter only analysis? Do you include that? Or?
So that varies completely. In the context that it's a power law, that varies. Is that what you mean? In other words, its normalization and its power law index vary of the concentration-mass relation.
For instance,
Yeah, that's exactly what's done here. I've just let it vary as any power law.
Oh, sorry. What I'm thinking is you're measuring the adiabatic contractor concentration, right?
Well, no. So let me back up. Maybe I went over it too quickly. So what I've done is I have 3 simulations. I measured what their concentration relation was.
Okay.
And I just demonstrated that it was an important effect. Okay, that was the first part. And then I said, well, I actually don't have the ability to predict what this should be to within the accuracy of these measurements. But I have some sense of what these modes by which the power spectrum should change due to this effect should be. In other words, we think the power spectrum will change primarily due to just an enhancement or a decrease in halo concentrations. But exactly what that enhancement or decrement is depends on the concentration-mass relation. So I've allowed that to float and be self-consistently determined within the same constraint problem. Does that make sense?
I guess I just think we'll never predict what this effect is.
Oh yeah, that's fine. So I haven't assumed that we don't know. Okay.
But I think we may be able to predict what it is for a given dark energy model in the dark matter only. So.
Oh yeah, sure. So that's kind of the underlying thing here is that maybe we can understand this in some parsed. So that's basically future work. We're going to future work. So we're starting a simulation campaign to get at some of these effects. That's basically one of the things you can start thinking about is can you somehow parse this in some way where you run a large suite of n-body simulations and then just add some modification that you understand on top of that in order to account for effects like this, if that's what I think you're saying something like that.
I think so. I think I'm saying something.
I mean, the other thing, obviously, is you can start just putting priors on your C of M relation. So I think recent papers are already approaching. So a prior of something like 30% or something like that starts to actually make you do a lot better. If you can put a prior on the amplitude of the concentration power law. And I think we're starting to even approach that with the Sloan data, for example, galaxy-galaxy lensing data. But basically, this is something to look at in more detail, how you can use nonlinear, quasi-linear scales to get cosmology. And I'll stop there.
Okay, one or two more questions. Yes, Lan?
Was your model equally successful for the case with cooling and cooling?
Yeah, it was. Yeah, as long as I cut it at L of a few thousand, it doesn't work beyond L of a few thousand because then you're starting to look at the structure of the galaxies, the substructure, things like that. So out to L of a few thousand. Yeah.
And the main effects on basically the power spectrum comes from these very massive layers.
Yeah, around 10 to the 14 solar masses. Yeah, that's right.
Yes, sir.
I just wonder, so you've got the errors, the biases on parameters down to around the 10% level.
Mm-hmm.
Have you got ideas as to what another modification you might make that would help you get even closer?
Very qualitatively, yeah. So there are some things that we couldn't actually get at because of the limitations of this simulation set that we're hoping to get at within the next year or so. But stuff like what Roman said, that the masses are slightly changed. The biases of halos have slightly changed, things like that. So there are small sort of quasi-linear effects that we could imagine starting to play with that might help to do that, yeah.
You know where it is in K rather than L that you start getting 10%?
Start getting 10% sort of enhancements?
Yeah.
I have the plot. I don't know. I mean, it's probably something like K's of 0.5, 0.6, 0.7, something like that. But I tried cutting in K space and L space. It didn't actually make too much difference. So I tried all the tricks that were in Hooter and White. It didn't make much difference how you cut the information out, if that's what you're asking.
All right, so let's thank Andrew again. So our next